Okay, we're back with our next video, third video from week 1. We're going to talk here about properties of a set of postulates. So, we got this set of postulates. Well, what properties could they have? Well, there are three main ones that you would normally like it to have, and it's to be, for the set of postulates to be consistent, independent, and categorical. If it's not, the opposites of these are inconsistent, dependent, and non-categorical. So the first and most important one is consistency. So you want a set of postulates to be consistent. What does that mean? Well, that means that the postulates do not lead to a contradiction. If the set of postulates was inconsistent, then you should be able to prove a statement both true and false, which is, of course, impossible. And so that leads you to a contradiction or a logical problem. Okay, and so we cannot have an inconsistent system. An inconsistent system basically collapses. So you want your set of postulates to be consistent. So how do we show that? Well, you want to show that they don't lead to a contradiction. Well, how do you know? Sometimes it's not obvious that they contradict each other, or that they lead to something that's a contradiction. So one method of showing that a system of postulates is consistent is to build a non-empty model that satisfies all the postulates. So you come up with some model, a physical model perhaps, for geometry, and it will satisfy all of the postulates. If that's true, it's consistent. Now there might be more than one different kind of model that are not the same in any way, they're not consistent with each other, but they're still consistent with the set of postulates. That's okay. But the set of postulates must be consistent. Okay? Now, we have different kinds of axioms in a set of postulates. There's different kinds of postulates. You have some that are called existence axioms, and those are ones that guarantee the existence of something. And you're going to need probably one of those in your set of postulates in order for you to actually have anything. Otherwise, you might just be talking about the empty set. Rather boring topic there. Okay, so you need some sort of existence axiom to guarantee that you actually have something in your system to be talking about. For example, something that says there exists some number of points or lines or something. But most of your postulates are going to be conditional postulates. They're going to say if something exists, then something else exists. Now, they may not always be written that way, but you can often rewrite them. In fact, a couple of the tasks that you have in this set of homework set this week is to take a series of statements that might be postulates or they might be propositions in some geometry and rewrite them in if-then form, even though they're not really written in if-then form, or recognize that they are existence postulates if that's the case. Okay, the second characteristic that we're going to talk about is independence. Now, we would hope that any set of postulates that we would be working with would be consistent. But when we take independence, what we're talking about is one postulate compared to the others, whereas consistency, we're talking about the whole set of postulates as a whole. So in independence, you're talking about one particular postulate in your list versus or compared to all of the other postulates. So it could be dependent or independent, and still be consistent. So, for example, if it's dependent, that means you can actually prove it as a consequence of the other postulates. Now, generally we don't want a postulate to be dependent on the others. We want our set of postulates to be sort of as lean as possible or sparse as possible. So we want to put just the minimum down there. The same thing's kind of true of our definitions. For example, there may be lots and lots of properties that a rectangle has. For example, a rectangle, you may say it has 4 right angles. Not only are all angles congruent, but all 4 right angles. It has 2 pair of opposite sides. It has 2 pair of opposite sides that are congruent. The 2 pair of opposite sides are also parallel. The diagonals are congruent. The diagonals bisect each other, yada, yada, yada. You could have a whole bunch of things. Well, you could put all those things in the definition. Okay, but then to say something's a rectangle would imply all those conditions, but then also to show something's a rectangle, you would have to show all those conditions are satisfied. So what we like to do is put a minimal set of conditions in our definitions, and the same way is true with our postulates. We'd like to have the minimal set of postulates that's going to produce the geometry we want. So we don't want a postulate in there that we can prove from the other ones, usually. Sometimes you'll see a postulate put in there that's dependent on the others because deriving it and proving it is beyond the scope of the intended reader. I've seen this done in high school texts when they'll take, for example, the side-side-side theorem from study of Euclidean triangles to be a postulate because they don't want to go through with the proof, although the students at that level could understand a proof, as we'll study later on in the course. But generally speaking, we don't want a postulate to be dependent. So if it's independent, it cannot be derived or proved from the other postulates. Now, how do we show something's independent? Well, that's a little bit harder. And so what we have to do to show it's independent is to produce a model showing the consistency of the system, okay, including the postulate that we're looking at, but then also produce another model that's consistent with all the other postulates, but which violates the one in question. If we can do that and show we have two consistent models, both of which are consistent with all the other postulates, but in one model the postulate that we're worried about or considering is satisfied, is true, and the other one it's false, then we have shown that that is independent. One of the big themes of this course is the people trying to prove Euclid's fifth postulate, and if they could prove that, then they would show that that postulate was dependent on the others. The problem is it turns out that that postulate is actually independent of the others, and it took many hundreds of years for people to realize this. And eventually what happened is, the only time that this happened is when we finally figured out that it's independent because we came up with another geometry, hyperbolic geometry, that was consistent with the other postulates, and then but independent of this. And it was even after they discovered hyperbolic geometry that they came up with a more physical model of that, which we'll actually go over the model first as we introduce hyperbolic geometry, not like the book does. The book goes, your textbook by Greenberg actually goes through the history of it, and it kind of unfolds the way it actually did in history, where they discovered some of these things before they actually came up with models. It's a lot easier to see what's going on when we actually have a model in front of us. Now, the last property that a set of postulates could have that we're going to talk about is it could be categorical. And to be categorical means it's basically a complete set of postulates so that there exists only one model up to isomorphism for a system. Maybe we need to talk about this word isomorphism just a bit. So in mathematics, you should be familiar with the word bijection. A bijection, of course, is a one-to-one onto function. So it maps one set onto the other set in a one-to-one manner. Okay, hopefully you know what all those words mean. But a homomorphism basically is a structure-preserving mapping. So homomorphism is something that preserves the structure. Well, what does that mean? Well, if it's a group, then in algebra you've got basically one operation in both the original group and the new group. And basically it's saying if you multiply two elements in the first group and then find their product and map that over to the second group, you should get the same thing as if you map the two elements over and then do the product in the new group. You should get the same element. It preserves multiplication. So it preserves the structure of a system. If it's a ring homomorphism, it's got to preserve both the addition and the multiplication. If it's if it's a graph homomorphism, it's got to map vertices to vertices and edges to edges in such a way that incidence is preserved. And in the case of a geometry, what that means is it basically maps points to points and lines to lines such that the inclusion of points and lines are preserved. So it's got to preserve the geometric structure. So that would be homomorphism. If it's isomorphism, then it's bijective homomorphism. So basically, when two things are isomorphic, basically they're the same thing. You've just basically renamed them. Rename the parts. And although they may look very different in some models, they actually turn out to be basically completely equivalent. So we're going to look at like 3 different models, physical models for hyperbolic geometry that are all isomorphic to each other. We're mainly going to be using the Poincaré Beltrami half-plane model in class, but we'll also look at, for example, the disk model. And those two are isomorphic to each other. So if there's only one model up to isomorphism for the system, say a geometry, then that set of postulates is categorical. And to show it's not categorical, we could take 2 models that are consistent with all of the postulates and then somehow show that they're not isomorphic. So we'd have to show that there's sort of some theorem that works in one but doesn't work, or some statement that's true in one that's false in the other one, and yet they still satisfy all the original set of postulates. That would be if it's non-categorical, you could do that. Now, there are times that you could want a system to be non-categorical. For example, the basic definitions of some basic big structures, for example, in algebra, when you define a group, you basically have a set and some operations, okay, or one operation, and that operation has certain properties, okay? And you make that very non-categorical in the sense that there are many, many groups that satisfy that definition. And you want it to be that way because if you prove something about groups in general, then it's true for all groups, not just one specific one. When we get to classifying shapes in geometry, we would like a hierarchical system of shapes. For example, when we get to quadrilaterals, we've got quadrilaterals. If we prove something for quadrilaterals, then it's true for every type of quadrilateral. And we want to define trapezoids in such a way that the properties we can prove for that are true for any subcategory. So sometimes you want things to not be categorical, but if you're defining a set of postulates for a whole system like a geometry, it's nice if you have them categorical because then you can, you've narrowed it down to one specific system. We're going to go for a long time in this course working with a set of postulates up to a point. They're going to be valid in what we call neutral geometry. And neutral geometry is going to include both hyperbolic geometry and Euclidean geometry. So anything that we can prove in neutral geometry, a non-categorical system of postulates, that's going to be true for both Euclidean geometry and the non-isomorphic hyperbolic geometry. Now, then at the point we get to a certain point, then we'll actually introduce an axiom, 2 versions of it. One will lead us to Euclidean geometry and the other to hyperbolic geometry. And so, anyway, sometimes we want to be categorical, sometimes we don't. But if you do have categorical system of postulates, then they completely determine the entire system. And there's basically only one model up to isomorphism.